Good morning, everyone. My name is Enrique Bosch, and I work for Inerco. I hope you can hear me and see me well. You should be looking now at the presentation, the first slide, webinar, technologies for NOx reduction in India. Welcome. First of all, from Inerco, we hope that you and your families are safe in these unprecedented times that we are living everywhere. And I also wanted to personally thank you for attending this webinar. I hope you find it interesting and productive. The webinar is going to take 40 minutes, around 40 minutes, and then we'll have 10 minutes for questions and answers by the end. You can make the questions using the GoToWebinar platform. Just send the questions and we'll try to reply all of them by the end of the webinar. If for any reason we can't do it, we will reply individually by email later during the week. You can also contact us using the email infoindia@inerco.com or using the phone number indicated on the screen. Okay. So let me start by saying a few words about Inerco, the company. Inerco is a group of companies with offices in 9 countries. One of those locations is in New York States, US, where I'm located. Now is 12:40 a.m., more or less. But as you see in the slide, we got offices everywhere. Okay. We are around 650 people, and our average revenue is 65 million US dollars. We invest a lot of money and resources in R&D, and that's the reason why you're going to see some of the technologies I'm presenting here today have been developed and patented by Inerco. Also, the company is structured in 3 main activities: engineering, technology, and environmental consultancy. Within the technology group, there are like 5 business lines. Combustion and environmental technology is the one we're going to focus today. We also have SEMS, continuous emission monitoring system. We also have acoustic solutions, water treatment, and soil remediation. In India, we have an agreement with the local company Unicorn Engineers. They are providing us with resources and capabilities for the Indian market. And I would like to introduce Mr. Ram Shankar from Unicorn. Good morning, Ram. How are you?
Good morning. I'm good. Good morning, Enrique. Good morning, everybody.
Would you like to say a few words about Unicorn?
Yeah. So, first of all, I welcome everybody for this webinar. And my name is Ram Shankar. I represent Unicorn. And we are actually a company who manufacture air pollution control equipments like electrostatic precipitators, bag filters, bag houses, and ash handling systems as well. And we are based out of Coimbatore. We've been in this field for 30 years, and we tied up with Inerco. I think we've been talking with them for the last 3 years, and we've tied up in 2019, early 2019, and with the tie-up, we bring a one-stop solution for all pollution control issues to India. And I hope this webinar is very informative and resourceful and interesting for you. And keep your questions posted so we'll get back to you as and when possible. Have a great day. I think Enrique,
Okay.
you can
Thank you. Thank you, Ram, for those words. Now that we have done the introduction, I'm going to switch off the cameras and I'm going to start with the content of the presentation. Okay, so first we are going to review the environmental framework in India, just a few words. Secondly, we'll go through the technologies, the combustion and low NOx technologies. And then I will show you a very interesting part, which is the case studies. So we'll show you some examples of the way to go, okay? So I'm gonna start with the environmental framework in India. So in 2015, the Ministry of Environment and Forests released the new emissions standards for the TPP thermal power plants, covering particulate matter, SO2, NOx, and mercury, as you see in the table. The limit was based on the year of commissioning and the boiler size. You see here the differentiation. And for NOx, initially, the limits were 600 milligrams per normal cubic meter for units before 2004, 300 milligrams for units before 2017, and 100 milligrams for new units after 2017. During the last year, there have been a lot of discussion about the implementation of these standards, especially the 300 milligrams limit. And it seems that in May last year, it was approved to raise the limit from 300 to 450 milligrams. This is what we see here. Since the beginning of the year, there is a lot of push also, especially from utilities, to increase the limit, the 100 limit, to 450 milligrams. Okay, so there is a lot. So they're pushing to move this number too, arguing that the technologies for 100 milligrams are not suitable for the Indian coal. So we'll see what's the final decision, but in the short term, the standards are going to be somehow relaxed. That's what I'm trying to say here. Comparing the implementation of the environmental standards with other countries or regions like US or Europe, in those regions, these have been applied in different phases. So normally it takes around 10 years to implement phase 1 and phase 2. That's what we have seen in the US and Europe. So my guess is that in the long run, all these limits I'm mentioning here, I'm going to be review again, and there will be more strict standards to be implemented. But like I said, it's going to take 10, 15 years to see those numbers coming to an end. So in this diluted scenario, we got two groups of technologies. The first one is primary measures, which involve the reduction of NOx generation. These are low NOx burners, stratification systems like OFAs, and combustion optimization systems or combustion optimizers. I'm going to avoid non-usual techniques like reburning or flue gas recirculation, as I want to focus primarily on the most extended technologies. The second group is the secondary measures, which are applied after the combustion and once the NOx has been already generated. These are the SNCR, or selective non-catalytic reduction, and SCR, or selective catalytic reduction. So I'm going to go through the technologies now. In first place, I'm going to talk about combustion modifications, LMB, low NOx burners, and OFAs, over fire airs, or SOFAs, separated over fire air. So the objective of this technology is the reduction of O2 content in the first part of the combustion, where the majority of the NOx is generated. This is what they call superstoichiometric conditions. It's also tried to reduce the amount of fuel that is combusted at maximum temperature. So there is a number of different LMB designs like recirculation, split flame, dual nozzle with the swivel mechanisms, and so on. So all these designs try to get the objectives I just mentioned, all these three here. The definition of these solutions cannot be evaluated locally at burner level, and this is what I try to represent here. Because the modification of the burners is going to change the combustion profile, and will impact in the boiler performance and operation. So this is an iterative process with several LMB designs that are tested, and then the results feed a model of the whole boiler. This is what I call here overall boiler impact and assessment. So in all cases, there is a number of critical aspects that have to be evaluated here. So first, the velocities in the burner and air nozzles. We normally try to achieve between 30 to 40 meters per second at these locations to get enough turbulence and good mixing. The OFA, the overfire air, normally takes around 25% of the combustion air. So in line with that, it's very important to find a nice layout, a good layout of the OFA ports to guarantee the turbulence and mixing. And at the same time, we need to ensure that the pressure drop in the wind box is enough to achieve those velocities. So everything is important. Experience is critical in the definition of these solutions, but also is important CFD modeling capabilities for the whole process, for the combustion process. Both things are critical. And I will show you how we use CFD models in one of the case studies later. At Inerco, we have been working for almost 40 years on power plants with different furnace design, tangential, wall fire, downshot, different fuels, anthracite, lignites, bituminous, subbituminous coal, high ash content, high sulfur, natural gas, fuel oil, biomass. So I would say we can provide solutions for almost any boiler design. To evaluate the design, you need to consider a number of parameters. I try to put the parameters here. First is NOx generation. This is what you are trying to find or to look with the LMB and the OFA. But also it's important the temperature profile and the heat flux. We can affect heat transmission because this will result in less transmission at the furnace area and more in the convective area of the boiler. So if that happens, you're going to need more spray attenuation or even derating the unit. That's why it's so important. Also, combustion resident time must be controlled. We need to guarantee that our solution provides enough time for the particle to be burned. And failing this will result in more unburned coal and CO generation. As a consequence of more unburned coal and CO generation, you get an affection and heat rate, so you will have less efficiency. And also with high CO in the furnace, can produce severe corrosion in the boiler walls and slagging in certain areas. So that's why it's important also to evaluate all these parameters, not just the NOx generation. I've seen many units with a nice value of NOx generation, but everything else was in bad shape. And just to be clear, every boiler is different by design, by operation, or by the fuel they are using. So it's special attention to has to be considered in the design stage. Okay. We're going to the next slide. I'll show you. Yeah. So when the design is done, we can manufacture the burners. Here, well, the burners, the OFA nozzles, and the ducts. These are pictures of our low-NOx burners. Some considerations here are the manufacturing procedures and material selection to guarantee the performance, but also the durability of the equipment. You have to consider also assembly considerations, shutdown period, and commissioning. And especially in coal applications, all the mechanisms that these burners have must be reliable and last for the very dusty environment they are exposed. Nobody wants the brand new burners that cannot action the registers a few months after the commissioning. So at Inerco, we also do burner upgrades. For example, in the pictures below, we modified or substitute only the parts of the burners that were required, not the whole thing. This is something that can be done in some cases, and when you have enough operating data and also you have worked enough time in the plant. Anyways, low NOx burners technology allows for a reduction in the range between 30 to 60, almost 60%, depending on how complicated is the design and the furnace modification. So moving to the second, well, there is an interesting concept about combustion modification that I would like to explain today. In conventional burner systems, there is a number of situations where the operation requirements impact negatively in the boiler performance. This is what I'm trying to show on the left. For example, when you have one of the intermediate mills out of service, for example here. In these cases, if you want to reach full load, you need to function with the other mills. And this situation here results in a gap in the combustion area here. And this is not good from the process point of view. The first thing we're going to see is an increment in NOx generation because there is less stratification in the combustion. OFA nozzles get closer to the coal in this situation. The second thing is that the furnace exit gas temperature, or FEGT, may increase importantly. This is because the combustion has moved up. More FEGT means more spray temperature, and even sometimes you got to derate the unit. So basically, we are moving the combustion up. In this situation also, there are less residence time for the coal particle to be burned, so we can expect more LOI, more unburned carbon. And the results also impact efficiency. You're going to have worse efficiency, and because you also have more CO, you're going to have probably some corrosion and slagging episodes. So not good to the situation. So looking at these restrictions, we developed the Flexicon LMB technology. Flexicon is a retrofit of the coal distribution system to create a low NOx system by connecting mills and burner elevations. So what we're doing here, the first modification consists of the connection of all the mills. So in this case here, if you look at the screen, you can see that all the mills are connected, and it doesn't really matter which mill is out of service because we can always substitute with another one. So the burner elevations are independent from the mills. This is always the same situation no matter which mill is out of service. It's always the best picture from the combustion point of view. The second modification is the addition of one of the burner levels to the others below. With this, we are concentrating more the combustion in the bottom of the boiler. And this has a dramatic reduction of NOx generation because, as we see here, we got much more distance between the coal and the OFA ports. So this is more like a sofa, separate overfire air. And the distance has increased a lot. The second is that you have a much better control for the FEGT, and there is no modification where the mills are changed, or even by concentrating the fire build down, you're gonna get better control. Also, you're gonna have more resident time. That's what I'm trying to say here. You get more resident time, more time to burn the coal particle, less LOI, and at the end of the day, that results in a better efficiency of the boiler. Because you also have less CO generation, corrosion and slagging are improved. One important benefit of the Flexicon is that does not require the modification of the pressure parts. The connections are in the coal pipes out of the boiler, which simplifies a lot the shutdown periods. So this is a technology we developed and patented, and I'm going to show you one of the case study that we have used in particular. So next option or technology is combustion optimization systems and analyzers. This is also a good way to reduce NOx emissions. Historically, there has been neural networks that use a significant amount of data from the plant and provided to the operators with data and recommendations. That will be this scheme here. So you got a system collecting a lot of data and providing recommendations. So at Inerco, we also developed our own combustion optimizer, which is what we call Abaco. Abaco use features from the neural networks, but also implement advanced monitoring device like what I call here Opticon, which is a flue gas composition analyzer in the boiler, or the Abaco LOI for carbon in ash analysis. So with this information and based on empirical tests we perform at the plant, we configure an expert system that is able to manage the combustion in closed loop control by acting on the air register or the cold register when it's required. So Abaco is again a patented technology by Inerco and is also recognized as a best available technology for NOx reduction and efficiency improvement by the European IPPC directive, which stands for Integrated Pollution Prevention and Control. So before going to the secondary measures, let me mention briefly one very useful analyzer. That's the Abaco LOI. The Abaco LOI is an unburned carbon in flash monitor, although you can use also to do the proximate analysis of the coal. By measuring the LOI, we can look to potential fuel savings and also to guarantee the sale to the same industry. The system has been patented by Inerco and is based on the same thermogravimetric techniques that are used in the lab. That's why there is no calibration required and no affection by changes in fuel composition, operating scenarios, or interference with SO3 or ammonia. Okay. The system is installed close to the ESPs with one analyzer and a number of these sampling models. And you can install a number of these samples and have a nice LOI map of your unit at different locations. So going to the secondary measures, SNCR, it's selective non-catalytic reduction. That means a secondary measure means that the NOx is already generated. So we try to reduce it by using one technique, and in this case is by the injection of ammonia-based reagent in the furnace. Normally, the reagent is ammonia water, 20-25%, or urea up to 50% in concentration. Both reagents are valid, although there is more applications in coal generation with urea, as urea gets better mixing because it takes longer to decompose into ammonia, and also the urea droplet penetrates more into the flue gas streams. Anyways, the injection of the reagent has to be done in a specific range of flue gas temperature, something between 900 to 1150 Celsius. Normally this is in pieces, this is above the nose of the boiler. Again, the injection process is critical to ensure the proper mixing of the reagent and also to provide enough residence time for the reactions. That's why, again, we rely a lot in our CFD capabilities. We do a lot of these models so we can test different injection strategies in different boiler conditions. Remember that you need to have the system running in all operating conditions. What I say here, in different boiler loads, XSO2, and those things. At Inerco, because we are experts in the combustion process, we can easily integrate the SNCR in the control operation. And also because we know specific characteristics of the combustion like NOx or CO profiles, we can differentiate the injection by areas or by injectors, maximizing the reaction and reducing the ammonia slip. Ammonia slip is the ammonia that does not react in the boiler because the process is not at the right temperature, or because maybe the mixing is wrong. So ammonia slip has to be carefully controlled, also because in coal applications can react with SO2 and SO3 and produce ammonia bisulfate, which is a very sticky and corrosive component, and this may affect very, very badly the air preheaters. So this diagram here shows the equipment required for the technology. And storage tank, normally for 10 to 14 days, pumps, distribution skids. SNCR normally can provide something between 20 to 40% reduction depending on the boiler size and the mixing capabilities and design restrictions. So gonna try to summarize all the concepts I have explained in this webinar so far. So I prepared this table. Here I'm representing the NOx emission scenario that the power plants are facing with the limit they have to achieve. The technologies or combination of technologies required to move in that direction. We are also considering a normal baseline between 700 to 900 milligrams per Nova cubic meter for the Indian plants, which is very typical. And I'm in a very, let's say, willful attempt to compare the capital cost of the solutions. I'm also indicating this column here, the relative capital cost, comparing everything with a low NOx burner system, okay? So for the 600 milligrams limit, we envision units using combustion optimizers and or minor furnace modification. Okay, this has a relatively low cost of implementation, but also there will be many units requiring low NOx burners. This will become the new standard as the units going to 450 will require this solution in most of the cases. And then we have two more scenarios that, as I mentioned at the beginning, are still not clear. So we don't know what will be the environmental decision. It's the 300 and the 100. The 300, again, LMB plus combustion optimizer or furnace modification may be what is needed in some cases, but in other cases, it will be required combination with SNCR. So we're gonna see a combination of these two technologies. The most restrictive scenario, 100 milligrams, will require LMB and SCR, selective catalytic reduction, that I have not mentioned today in detail in my presentation, because this will be the technology to require in the less probable scenario in the short term. So SCRs require the construction of a reactor with catalysts. The retrofits are normally complex projects, and as you can see, the relative capital cost is pretty high. However, these systems are widely implemented worldwide, and they are one option that I envision more in the long term. So not in the short term, but in a few years. Okay, but that's what we envision for these limits. At Inerco, we can provide with all the technologies I mentioned. We perform combustion diagnosis and warranty test. We have an extensive experience with different fuels, with different boilers, and we also have our own CFD capabilities. We can supply all the technologies commented: low NOx burners, OFAs, the Flexicon, monitors like the Abaco LOI, SEMS, continuous emission monitoring system, our Abaco combustion optimizer, and also for secondary measures we can do SNCRs and SCRs. So we have all these solutions for the NOx. So now I wanted to show you a couple of case studies with more detail to illustrate what we are talking. Okay, so this is one case. Boca Mina power plant is in Chile. It's a tangential unit, 127 megawatt size, with 4 mills and 4 burner elevations. Originally, the NOx baseline was 550 milligrams per normal cubic meter. Of course, always dry basis at 6% O2. And the objective of the project was to reduce emissions below 400 milligrams. Okay. And we did a bunch of things in this power plant. The first thing we did was to install new LMB, new burners. So you got here a picture and drawings of the burners we install. We also install a sofa, a separated overfire. This is a picture, an actual picture of what we installed there. This sofa also have a yaw mechanism to adjust the angle of these nozzles. And you see here some drawings of the sofa ducts coming from the secondary air ducts to the sofa openings. We also improve cold distribution, some modifications in the cold side. We also did improvement in the air preheaters, installing a cleaning system and also a double sealing system. And we also have to do modification at the wind box because the power plant used to have some issues working at minimal load, so really low pressure at the wind box. So we did some modifications to work well at low load. The result was emissions achieved below 400, actually 390 milligrams per normal cubic meter. And the good news is that they are only using half of the capacity of the OFA. The OFA was designed to use up to 25% capacity, and they're using 13%. The CO was controlled below 100 ppm, and also LOI and heat rate was maintained. Okay, so this is one good example for low NOx technologies. The other technology is the other case study is Lada power plant. This is a power plant in Spain, 350 megawatts opposed wall fire boiler with 5 mills, 5 plus 5 burner elevations, and a baseline originally was 700 milligrams per normal cubic meter, and this was very challenging because the objective was to go below 200 milligrams. Okay. Also, this plant had some operating issues like slagging in the areas close to the burners. Also, the top burners were damaged, and also some corrosion in the side walls. And again, here we installed a lot of technologies. And here we're going to talk about the Flexicon too, because this is the previous situation of the boiler. The boiler has 5 mills. They need 4 mills for full load, and they can reach full load using this configuration or this other configuration. So these two options. Oops. So what we did is because this boiler is super short, is really short, we cannot install an OFA or a separated overfire. There is no room to install new ports. So what we did here is we applied the Flexicon concept, the Flexicon technology, and we concentrate in the lower levels all the combustion process here on the right, and we use the burner ports as a sofa ports, as here. Okay, so this way we can have a sofa without doing any new ports, and it was the only solution for this boiler because it was very short. So again, this is an example how we use the CFD. There was a lot of design work, a lot of CFD work. We tested different burner designs. You see here different tips. We studied different geometries, materials, and local NOx generation. And having that, we did the furnace assessment, studying the overall NOx we were getting, the heat transfer, velocities, carbon in ash, CO generation, and corrosion. What I'm presenting here is on the top, I'm presenting the temperatures. So because we have to decide which ports we're going to use for the OFAS. So at the end of the day, we went with the third option, which is one elevation in the frontal side, another one in the rear for better mixing. Also, we studied what was the O2 concentration close to the walls. We need to protect the side walls because there was some corrosion in the combustion area, the bottom part, and corrosion is produced when you got nearly zero O2, high CO in those areas. So we really need to see what was happening there. We install, I'll show you later, we install what is called curtain air to protect those areas, and we also study CO generation. So we installed the new burners. We modified the windbox for this new burner configuration. We installed what I just said, the curtain air. This is a small amount of air we inject in the side walls to avoid corrosion. Okay, and also we did all the connection with the Flexicon. We connect all the mills the way I explained before to have always the same configuration at the bottom part of the boiler. Okay. For the SNCR, we installed this system. You see here all the equipment, different distribution skid, water dilution skid, and other equipment. Also a storage tank for urea. I think it was for 2 weeks capacity. And at the end of the day, what we got in Lada, remember we have a baseline of 700 milligrams. And what we got in Lada, it was a result of 240 milligrams per normal cubic meter only with primary measures, with the combustion modifications. And using the SNCR, we were below 170 milligrams per normal cubic meter, which is a great reduction. So I'm gonna just mention 4 more case studies, not with all the detail. We got Los Barrios power plant. This is a tangential unit, almost 600 megawatts. The baseline was 800 milligrams, and only using the Flexicon LMB technology, we were able to go below 450 milligrams per normal cubic meter. The other one is Battle River. Battle River is in Canada, power plant in Canada, 405 megawatts. The baseline was something between 500 to 800 milligrams, depending on load. And using the Abaco, the combustion optimizer, we were able to improve the heat rate 0.5%, and also to reduce NOx between 15 to 30%, depending on the situation. And the last 2 cases is Velilla power plant. This is a 360 power plant with a very high ash coal. When I say high ash coal, it's similar to Indian coal, about 40% ash content. The baseline was really high, 2,200 milligrams when we started there. By implementing different technologies, the Flexicon, the Abaco, burner upgrade with OFA, we were able to reduce below 490 milligrams per normal cubic meter. And the last example, we have Barranco and Granadilla. These are 4 units, small units, 80 megawatts. They used to have dual burners, coal and fuel oil. So we modified the burners to only fuel oil. Originally they had 420 milligrams. With primary measures, we were able to reach 200 milligrams, and with the SNCR, we were able to reach below 150 milligrams per normal cubic meter. Okay, so these are the case studies I wanted to show you, and also this is the end of the webinar. Thanks for your attention, and I think we have some time now for questions. Let me see. Oh, let me see the questions we're gonna have. Okay. Well, we have an interesting number of questions. So let me activate the camera again. Okay, Ram, if you want to be here. Okay, so we got one question about the SNCR. And what is the limit of ammonia ppm for SNCR at the exit flue gas? Well, this is a good question. Ammonia sleep, as I said before, has to be controlled because of the ammonium bisulfate generation. Normally, the limit of ammonia sleep asked is depends on the technology. So when we are talking about SCR technology, it's normally something used to be 5 ppm. The most restricted value is 2 ppm. The standard now is 2 ppm, but something between 2 and 5 is normal. When we are talking about SNCR, SNCR typically is something between 5 to 10 ppm. Below 5 ppm is difficult to guarantee in all the scenarios. Can be done, but it's very, very tight. But the normal is below 10 ppm. So something between 5 to 10 ppm is normal. You have to consider something. Ammonium bisulfate depends a lot on SO2, SO3 content, and that depends on the coal quality. So you need to consider sulfur content of the Indian coal. Our experience is that it's not the worst coal for sulfur content. So in other words, those limits have not to be the most restricted ones because there is no much sulfur in the coal. Okay. So I try to reply the question about the ammonia sleep and also the ABS formation. Okay. Yes. Got another question here. Optimum temperature window for urea injection in atmospheric fluidized boiler. Good question. Well, the range is something for urea is something between 900 to 1,150. The good thing is with these boilers, normally they have more residence time. So I've seen applications where you use ammonia instead of urea for those applications because the boiler configuration allows you more residence time, and the efficiencies normally are very high. But you need to move in that range of temperature. If you inject below that temperature, you're going to have ammonia sleep, and if you inject above that temperature, you're going to generate NOx. That's the opposite of what we want to do. Okay, I have more questions here. Does Inerco provide emission guarantees? Yes, we do, and we provide the warranties, and also we got our own LMB technology. This is another questions. We got different designs and different partners also. So, but the LMB is something we do and we manufacture. What will be the impact on boiler efficiency when we do a modification with low noise burners? Well, I have seen this many times. When you have a modification, a combustion modification, you're normally trying to reduce NOx emissions. You may improve. You may increase the LOI. the unbound cold. So at the end of the day, if you are affecting that parameter, your efficiency is going to be affected negatively. So I think I mentioned this before. The problem is not just the NOx value you're going to reach. I would say that's not the easy part, but that's easy. The problem is to reach that value by maintaining the rest. So not worsening LOI, not worsening CO and other parameters, not worsening heat transmission in the boiler, things like that. So those are all the things you need to consider. Okay, and I think we may have time for one more question or two. How are you controlling the ammonia corrosion during non-operating hours? I really don't understand this question. Ammonia corrosion. Where during non-operating hours, the system is shut down. So if you have in SNCR system, when you have the injection well designed and your injectors are mixing well the ammonia or the urea, you shouldn't be injecting through the wall. So you're not going to have a corrosion problem unless you have a design problem, unless you are injecting too close and you are impacting, your droplets are impacting the wall. You shouldn't be having any problem. And when these non-operating hours, you are not injecting. Okay. Also have, I think maybe we have time for one more question. I have one guy who was interested in knowing about SCRs. I know I haven't talked about SCRs because it's the less probable scenario, but SCRs application, there is a lot of concerns with high ash coal. I have seen this many times, but the short response is that there is not a big deal with that. So it's true that high ash coal can degrade the catalyst, can reduce your catalyst life, but there is like different configuration of SCR system. You have the high dust, low dust, and Thailand. If you go to low dust or Thailand, problem solved, because the ash content is not gonna reach the catalyst. And also, even if you are in a high dust configuration, you can install cyclones and you can install some equipment to reduce 50–70% the ash content before the catalyst. So at the end of the day, it's a problem that it can be solved. Okay. Okay, so well, I tried to replay a lot of questions, but unfortunately, we're running out of time. So the rest, I will reply personally by email later this week. Yes, well, thank you very much, everyone. Like I said, if you want to contact us, you have our information here. info.india@inerco.com, and also the phone number. You can reach Ram Shankar anytime. He's our representative in India. He will be in touch with you. So any inquiries you have, you can contact him. Okay, Ram, you want to say something before closing?
Yeah, I think we have some more unanswered questions. So I thought we'll reply to your questions personally. And I think you have my contact number and the email IDs are already there. So you can just drop in and we'll be very happy to answer your questions. And I think that's about it. So I think we can put the email ID and the phone number again, Enrique, just in case they have not noted down.
Yes, the email is indicated in the presentation is info.india@inerco.com. You should also receive an email after the webinar with all this information and also with the presentation. So you will have the slides. And so it will be very easy, and you also got this local number to contact us, and they will pass you with Ram Shankar. Okay.
Okay. So.
Okay. Well, thank you, everyone. Thank you for attending. I really appreciate the time you have spent. I hope you have enjoyed the webinar. Probably we will repeat the webinar in the next month or two. Probably adding some more things. So really appreciate your time. Thank you, and stay safe, friends. Goodbye.
Bye-bye.